Okay, dear colleagues, ladies and gentlemen, I have the pleasure of introducing Klaus now, my colleague who made a presentation and wrote a paper on Exergy calculations for systems exhibiting solution phases as well as compounds. This should actually have been the first presentation at our users meeting, but due to circumstances beyond our control, we were not able to do that. Klaus was unfortunately not able to join us on that day. So nonetheless, we definitely wanted to record the presentation to make it available to you, so you at least have the possibility to follow the presentation online. So Klaus, please go ahead. And as a little extra, we can already tell you that the paper has been published already, and the link to the publication, I think it's a Journal for Sustainable Metallurgy, if I'm correct, is in the presentation. So if you're interested in the full paper, don't hesitate to call it up. Okay, Klaus, there you go.
Yeah, thank you, Stefan, and thank you everybody for joining. I'm sorry that it didn't work out at the users meeting, but sometimes other things have higher priority. So let's go into the story. Exergy calculations for systems exhibiting solution phases as well as compounds. I think the major point here is exhibiting solution phases, because the story concerning compounds is essentially already well established. But when I started working with Markus some time ago, we realized very quickly that that is really not the full story if you just treat thermodynamics or thermochemistry on the basis of compounds. So in the story I'm telling you now, I will be in the first part talking about the summary of the theory, which now includes solution phase formation. And then I will give you a case study for a pyrolytic slag system. You will see later why we have chosen that. I think it is now really the proof that using the method which I will be describing is the thing to do from now on. So let's go for a summary of the theory in terms of the definition of the exergy. And that is really now the statement by Szargut that was published in 2005. Exergy expresses the maximum work output that can be extracted from a system when it reaches equilibrium with a so-called reference environment in a reversible way. Now we have to talk about the reference environment. Essentially, that is embedded in the formulae. So let's have a little bit more in terms of explanation of exergy. It gives an idea of the quality of resources, that means of energy on the one hand, as well as the materials which are taking part in particular processes. Now, quality of resources, what can that be? If you talk, for example, about materials and you take as a case water, then you can take water from high up in the mountains, or you can take water from a sewer which actually flows into the sea. And you can immediately see there is a big difference in the quality of the water itself, because high up in the mountains it's clear and pure, whereas when it comes from the sewer, it is really not proper water anymore. But that is the one aspect of the quality. The other aspect of the quality is when it is high up in the mountains, it also has potential energy, which can be made to work in some way or another. And of course, when it has reached sea level, it's essentially only the waste which contain energy coming from the wind, right? So that is something which we have to keep in mind. The quality of resources is not just the pureness of some material, it's also other energies like kinetic or potential energies, which are part of that material. Then we have another aspect, and that is the work output of real-world systems includes irreversibilities, which can be quantified. And quantified in terms of, in the end, an energy. In other words, we can even give the irreversibilities a price, because we know how much we have to pay for a kilowatt hour. So that is really something which we have to keep in mind when we talk about exergy as a general method for judging processes and materials. Well, the contributors to exergy I have put into one slide. And as you can see, it ends with a box plus ... So what I have listed here is really just the major parts. Kinetic and potential exergy, I have already briefly mentioned a moment ago. When it comes to what we are interested in, it will be the middle of that slide, but let's also take into account in real-world processes, comminution, and even sound. These are related to energies that go into a process. But this is not part of this lecture, so let's focus on electrical exergy and heat exergy, and also the chemical and the physical part of it. And when it comes to electrical and heat, we do have to take them into account because in the end, you will see that later, we have to talk about energy that goes into a process, and usually people in the exergy world assume that to be electrical energy. But also, of course, there are exothermic processes, and they will release heat from the process, and then we have to take into account the Carnot expression, which actually scales down our enthalpy, or energy, if you like. So if we have 50 joules electrical energy, that is not equal to 50 joules heat, because of that scaling factor which comes from the temperature. And that, of course, means heat is a less valuable form of energy as compared to electrical energy. So we need to have a tool or a method or an equation, if you like, which we can apply to calculate the chemical and the physical contributions to the exergy. And the global term is what you see here. It is really a difference between two enthalpies, the one of the system at temperature T and the other one of the system at the reference temperature, which is room temperature. And the same holds also for the entropy. And then we have to multiply the entropy difference with minus the reference temperature. So reference temperature is 25 degrees C. That is the same as in our pure substance databases, or actually any thermodynamic databases, the reference state. And of course, T can be any value. And that means it can also be room temperature. And that effect, or that fact, we will make use of now. You see, when people started to look into the basic data of the exergy, they of course, looked into the elements, and then they also looked into substances, and that is essentially comparable to what we do when we set up a thermodynamic database. We have the unary data, the metastabilities from SDGs, and then we have the pure substance databases where we have enthalpy and entropy at room temperature and a CP function, right? So similar to that, we can actually now also work out an exergy relationship. And for an element, we can do it in the way that we say, okay, there is this element in the world, and there is this element in the pure state. Okay, so in this case, the world is indicated by a superscript 0. And of course, the world is at room temperature. So what we can do now with respect to, for example, oxygen, we can simply apply this formula. And what you would see is, of course, there is no contribution from the enthalpy, because in both cases, it's the enthalpy of oxygen at room temperature. And also, when it comes to the entropy, it's the entropy at room temperature in both cases, but there is a big difference now with respect to the partial pressure of oxygen. The partial pressure of oxygen for pure oxygen is, of course, 1, and the partial pressure of oxygen in the world is the oxygen partial pressure in air. So if we take away all those other contributions, in the end, what remains is that we have this RLN 0.21 term, and of course we can multiply it out, and here we get a value. Exergy of pure oxygen is 3.868 kilojoules per mole. And if you look it up in the standard tables, then you will find it isn't exactly the value which I have just given you. It is slightly different because the Szargut people did some fine-tuning for the oxygen partial pressure, and they come up with a value of 3.92. But essentially, that is now what we need to figure out. We have to have a very small database with the exergies of the elements in the respective state at room temperature. And if we have that, then we can continue working with combined substances, let's call them compounds, as we always do, and then we can calculate the exergy of a compound from the stoichiometric sum of the exergies of the elements contained in the compound, and again, a contribution which comes from this global term, H minus H0 and S minus S0, and of course that minus T0 term. Okay, so then what do? We look at the formation of the compounds at room temperature, and therefore our T value is now equal to T0. And then what happens is very obvious, right? Because here we have the enthalpy of our elements, and here we have the enthalpy of the compound, which, as you will immediately recognize, is equal to the enthalpy of formation of the compound from the elements. The same holds then also for the entropy term, and in consequence, because T0 is multiplied in here, we also have then a delta G0 of the compound. And that makes it easy to calculate for each compound the exergy based on the elements and the delta G of formation of the compound from the elements. Okay, so once the exergies of the elements are known, the exergies of any stoichiometric substance can be calculated by accessing a thermodynamic database. But yes, we now have an exergy of the compound. So can we apply this idea that from the exergies of the elements and a delta G0, we can get an exergy? Well, I called it the compound here, but of course it would then have to be an exergy of a solution. And yes, of course, in principle, we can do that because we can calculate for any solution phase what is the stoichiometric sum of the Gibbs energies of the phase constituents at room temperature, and we can calculate the Gibbs energy of the solution, let's call it alloy, at room temperature for that given overall composition. So again, we have a delta G0, but this time it refers to a solution. And of course, it will not be a single value then, but it will be a continuous range of values depending on the phase internal composition. But nevertheless, we can do something like that. And of course, if the constituents or the components of the solution are compounds, then we should really take an intermediate step and first treat the compounds on the basis of the approach for compounds, and then calculate the Gibbs energy of formation from the compounds. But in principle, that can all be done with straightforward calculations based on room temperature. So now we have to transition from room temperature to any temperature. And of course, we can then apply once again this global term, but this time we will really have to take into account a change in temperature, which gives us essentially a delta H and also a delta S. And how do we do that? Well, we calculate the integral for the heat capacity curve itself, and also we add enthalpies of transition in the respective temperature interval between room temperature and T. And then we do that very same thing with the Cp over T integral, and we get our term concerning the entropy change. Okay, so again, we are simply using our H minus H0 minus T0 times S minus S0 global term. Yeah, but in this case, T is not equal to T0. Well, then people suggested, and that is also in the publication of 2005, we can include solution phase effects. And they did that in the classical way, based on reaction thermodynamics, where you say, okay, I can calculate an activity which contains, I can get a chemical potential which contains the reference potential, which is essentially the Gibbs energy of the pure constituent, and a contribution from the activity. Okay, so they said, yes, we can calculate the room temperature exergy, we can calculate the high temperature exergy. Then we look at the activity at the species at high temperature, but also, of course, we have to take into account the activity of that respective species at room temperature. That will then be consistent with the equation which we call the global equation, right? But there is a problem. There is question number one: is it okay that the base state at T0 is assumed to be the pure components? In other words, all of these AI0 values are equal to 1. Well, There are cases where this would certainly be okay, right? If you take the CaO MgO system at room temperature, there is a gigantic miscibility gap. You have pure CaO and pure MgO. You take the iron chromium system, gigantic miscibility gap in the body-centered cubic phase. You have essentially pure iron and pure chromium. But these are, let's say, the few cases where you can immediately say, yes, activity equals 1 is fine, but that is not general, right? The other thing, of course, is when it comes to taking the activity at high temperature, what is then the reference state? For example, take a liquid which forms from two constituents that can be stable at temperatures below the two melting points. So what is then the reference state? Is it the liquid constituents, which wouldn't exist as pure substances in the liquid state at this particular temperature? Or do we take into account that the components are solid at this temperature and we then add the activities from the solution phase? Yeah, that is really now the question in the background, and you will see that we have taken care of that in the application case. And you will also see there is an answer if we say, why not use the global X term? We can do that. And then we don't need to worry about having two different states here, possibly. It will take, that will be taken into account all by itself, simply by looking at this global term. Okay, so there is this distinction again. The solution phase is stable at both T0 and T. The solution phase is only stable at T. At T0, another set of solid phases is stable, and that could be from the pure elements, or it could be an equilibrated state showing solid solutions or showing stoichiometric compounds. So that is really now very important to take into account. And as I already indicated, if we use the expression which you see on top of this slide consistently, and consistently means we always take into account the very same composition, but we can look at it as an equilibrium state at temperature T, or we can look at it as an equilibrium state at T0, meaning room temperature. Then everything is fine. So if we do it in this way, we would imply that there is chemical change and also physical change, and therefore we should simply call this expression now the physical-chemical exergy. And if we do it like that, then for the calculated equilibrium state at T0, the exergy needs to be derived in an additional calculation. We still have to apply those basic equations which you have seen in order to get either the exergy of a stoichiometric compound at room temperature or the exergy of a solution phase at room temperature. That has to be added into the calculations in order to get a complete expression. So now let's have a case study, and that is for a firelytic slag system. Now, firelytic slag system, that is already indicating a particular composition based on, well, people like to call it FeO and SiO2, right? And it is really 2 FeO, 1 SiO2, firelite. if we look into the phase diagram, then we will realize firelight is a high temperature phase. You cannot really make use of it at room temperature. That is one thing. The other thing is, depending on the conditions, and that is indicated in the second statement, conditions with respect to the oxygen partial pressure, we really need to figure out how much oxygen is actually contained in the system and how does that affect the actual phases which are stable at this high temperature, 1250 K. So what we have to do now is to figure out from those conditions in the first two statements, how can we apply Szargut for the reference state solid or liquid, and how can we apply the full works according to our general formula. So that is a step which needs to be taken into account in order to really get a full picture, because here the starting situation is that we have metallic iron, but we already have silica. In the end, we want to have a completely oxidized system, and that means, of course, there is reaction of the iron and the oxygen, which is exothermic, and that means in the end heat is released from the system, and therefore our exergy for the heat is to be applied, and it has to be added to the outgoing stream rather than the ingoing stream. Maybe the one or the other of you remembers that in the last users meeting, I was talking about calcium silica, and we started with the two oxides. Then, of course, you have to put electric energy in to bring solid calcium and solid silica from room temperature to a liquid state. But here, it's the other way around. There is an exothermic reaction. But how do we work out what reacts? We have to know how much oxygen we need in order to satisfy a particular oxygen partial pressure. So really, our simple view of the process would be this. We put iron and silica in. We can calculate an exergy for these. We can get hot slag out and also heat, but we don't know how much heat yet because we don't know how much oxygen yet. We only know the oxygen partial pressure. So in that case, we have to first look at our phase diagram with respect to oxygen partial pressure. And I hope you all remember this is now a type 1 phase diagram, where both axes are potential variables, and the one is the classical temperature, and the other one is the classical oxygen partial pressure. And then we have here somewhere 1250, and you can see, yes, there is a wide range where there is liquid slag. When you go to lower temperatures, yes, then you also find there is firelight possible, but it is at very low oxygen partial pressures, and it is also at reduced temperatures. Otherwise, firelight doesn't really play a role here. It's really just a name which people like to apply for these slags. Okay, so this firelight composition with respect to the iron to silicon ratio, that is given here. Yeah, but then when we increase the oxygen partial pressure, we leave the range of liquid slag. We come into a range where the oxides at the high temperature are all solids. That is now very important to keep in mind, because we want to, or we will see later, that this change of having a high temperature liquid into a high temperature phase combinations of stoichiometric solids, that makes a big difference, right? So the message from the phase diagram is the firelight is not the stable phase that we are interested in. and also the high oxygen partial pressure delivers a solid state even at high temperature. Now, if you look into the results of the calculation from Equilib, where you simply start with 2 iron and 1 SiO2, you fix the temperature to be 1250, and then you run the oxygen partial pressure through an interval, then you can go backwards, and from each of these calculations where the oxygen partial pressure was fixed, you get an oxygen amount which is necessary at room temperature in order to reach this particular oxygen partial pressure at the high temperature. So here we now actually know how much oxygen we have to put into the system for the given range of oxygen partial pressures. That is now the result of a proper one-dimensional phase mapping through the system. And you can see there is a vertical jump here where the oxygen amount changes at one value of the oxygen partial pressure, because we are changing from the range where there is a continuous increase of oxygen amount while the molten oxide is picking up oxygen. We actually jump into the region where we have a fixed solid state, slag, and there we do not need to change the amounts any longer. So what we now have gained from those introductory calculation steps is what we really need in order to define the exergy at the start, because now we know the oxygen amount, and also for the exergy when the system is equilibrated at the high temperature and we assume it leaves the reactor at this state, then we also know how much heat is evolved because we know the amount of oxygen. Yeah, what comes next? Next comes lots of Excel calculations based on the element exergies, the delta G0 values, and the H minus H0, as well as the S minus S0 values. And in the end, we can come up with this diagram where we can calculate the difference between the exergy in and the exergy out. Essentially, that means the exergy dissipation as a function of oxygen partial pressure, right? And you see here in blue, reference state solid, in orange, reference state liquid, and in the triangles, you see the values calculated from the global formula. Now here, obviously, there is an overall underestimation because we have to choose a reference state if we want to apply that equation with the activities. Whereas when it comes to oxygen partial pressures in the range of stoichiometric solids at the high temperature, there is now agreement between reference state solid and the actual H minus H0, S minus S0 calculation. And for us, that is really now the proof. Forget about those reference state discussions, which follow from Szargut's definition. Simply use the general formula all the time, and then you have all the time a unique number which tells you what the exergy dissipation is. So the two Szarguts overestimate or underestimate, and of course there is this transition between the slag range and the solid range, and now that is a smooth transition, as you can see from the triangles, instead of having a jump when we base the calculations on the two possibilities of Szargut. It's much better to have only one possibility which is consistent throughout. So as a summary, we can say we have, for a proper quantification of exergy of metallurgical processes, it is not sufficient to recur to pure substance contribution. That is quite obvious. The effects of solution phase formation need to be incorporated properly, not by way of trying to estimate activities, and but SAGE, of course, provides the basis for this. And we can apply that global term consistently, no matter whether we're talking about solution phases or compounds or combinations of them. We are simply describing a particular state of a system at a particular temperature T, and we compare the very same system and same with respect to the overall composition at room temperature with this. And then we can apply this general equation and get consistent answers. So we do not need to work with the reference state anymore. We can use, in this particular case, chem sheet, because it was just a single equilibrium zone. If you wanted to go to complex processes where you have several local equilibria interconnected, then of course you would start with a pi-based model, and that would indeed greatly advance the process modeling as it is done so far with software which can only handle stoichiometric substances. And in the end, of course, a more transparent and realistic dissipation of exergy in circular economy processes can thus be evaluated. That is the end of my story. And what Stefan already indicated is given on the next slide. In the Journal of Sustainable Metallurgy, published online June 18th, you can find that paper, which has the title Expanding the Exergy Calculation Methodology of Materials to Include Equilibrium Calculations of Complex Systems. And here is the link. And with that, I would like to thank you for your attention. And if there are questions, let's see what we can do about them.